Morning everyone and welcome once again. Today's first speech will be given by Kozcaz and his speech is entitled as Understanding Gauge Theories from String.
Physics days to talk about what I've been working on during my whole academic life. And it's going to be, I'm not assuming any prior knowledge about string theory, it's just going to be some overview about basically two papers I wrote back in the day. But my main motivation is to try to convince you that this summary here about string theory is inaccurate, that we actually have some idea what we can compute by just taking the point particles and make them strings. Okay? String theory is usually associated with Sheldon Cooper. Maybe you can turn off this light if possible.
Yes, of course.
Maybe this the first row. Otherwise it seems possible to see. Yeah, perfect. So yeah, I mean, for most people, when the name string theory, when they hear about string theory, they hear Sheldon Cooper, this egocentric genius string theorist from Caltech. Okay, and there's this interesting story between me and my collaborators and Sheldon. In I think season 7 or so, he decided that string theory is not going anywhere, that he wasted his time and he should go string theory. And one of my collaborators was forced to watch this episode to say, oh, why are you still doing string theory? And then he got bored and started looking at the whiteboards in their apartment to see whether they put meaningful physics on them. And as it turns out, he said, oh, that's a nice quiver diagram that we use to describe gauge theories. And then, oh, here are some geometries we use like in string theory, and there is like this cartoonish figure which tells us how to orient different membranes in string theory. And then he realized, actually, this is from our paper. So then we just search for this thing. So that this our brain configuration, this is the quiver diagram. And if you go to the next board, this is one of the equation partitions function we computed, and this is something. Oh, yeah, this is something I computed, and this is again some construction or some bundle structure that we use in our paper. So Sheldon decided to quit string theory apparently after he studied our paper. And here's the paper. It's called the on-orbitals of M string. So we were very delighted that we were such an influence. Okay, so we were not happy or we were not successful with Sheldon, so I gave another try with my daughter. So when she was younger, I just gave her this Bible of superstring theory, the book by Green-Schwartz written. So she looked a little bit surprised and didn't hesitate to give the proper reaction, like string theory. So okay, so today that's my end trial to change the sentiment or the reaction towards string theory. Okay, so let's start with some motivation. Okay, this is both historical, also related to what I want to tell you today. Okay, so one of the most fundamental problems we have been facing in theoretical physics, maybe over the last 30, 40 years, is to understand the low energy dynamics of non-abelian gauge theories. The famous example being the color confinement in QCD. We know numerically that quarks confine. We have seen in experiments that quarks confine, but if you want to solve this analytically, we haven't been so very successful. And there's even there's $1 million prize by the Clay Institute for people who can define field theory rigorously as well as can solve the mass scale problem. Okay? And we know that also the understanding of the interaction in QCD before QCD was also the main motivation for the birth of string theory. But after people formalized the QCD, which matches perfectly with the experimental data, and this is from 2012 by CERN, there are even more recent graphs which shows perfect agreement between the experimental measurements and the theoretical computations. Okay? So and then in 2004, even the authors of two papers, one by Gross and Wilczek and the other by Polisser, were awarded the Nobel Prize. And as I said, still, I mean, although this is an old theory from 70s, it's still not very well understood when you want to understand the low energy dynamics. So what do we do if we face a difficult problem? Well, we simplify, right? I mean, this is what we teach in our courses, Physics 101, to our students, right? I mean, we just start with this inclined plane, which doesn't have any friction, air resistance, heat, rotation. It's just a stupid block that just slides down the inclined plane. So we want to, like, you know, have something similar. So we want to, like, you know, we have a very hard problem we don't understand, and we want to try to simplify it. Okay? So we want to, like, you know, find a theory that is like QCD, but over which we have some analytical control. Okay? So, and then if we understand this cousin theory, I would say, then we can hope to maybe tweak or change our methods to understand the more complicated problem, which is the honest-to-God non-abelian gauge theory, QCD. And here, like, you know, I mean, that's the ultimate goal that I have in mind. Right here, like, you know, when we develop the three-bud diagram, we say, okay, let's add friction, then air resistance, and we just add more and more complication as we go along. So this is going to be our philosophy. Okay, and then if you search for cousin theories over which you can have analytic control, the supersymmetric theories are the ones that strike you immediately. And just a disclaimer, when I'm talking about supersymmetric theories, I do not intend to solve problems for which supersymmetry has been used widely, such as hierarchy problem or other naturalist problems. For me, or like, I'm not talking about superpartners being the dark matter candidates. I'm not talking about this kind of stuff. I'm just like, you know, taking this, okay, I have a complicated problem, its simpler version, its simpler cousin is supersymmetric theories. I'm just regarding this as a mathematical, rigorous, or like, you know, not rigorous maybe, but a mathematically controllable theory. Okay, so please do not ask me about whether I think that the supersymmetric partners are dark matter candidates. I don't have any comments on that. But then you can ask, what does supersymmetry does to the theory? Well, I just want to, like, you know, give another analogy from the complex analysis courses. So what actually supersymmetry seems to be doing is, it takes a real theory. So here we have an integral from minus infinity to infinity sine x over x that you want to solve, but you cannot solve it in the usual calculus courses. Well, if you take this integral and bring it to the complex plane, then you have these tools like residue theorems, which allows you to complete this integral, and you can actually solve this and get the answer for the first real integral. So this is more or less what, like, supersymmetry does. I mean, it adds more symmetries, but this addition of more symmetries brings some sort of complex holomorphic structure to the theory. When you are talking about holomorphic functions, you have all this machinery available for you from complex analysis. And as I will try to demonstrate soon, when people try to use this complex analysis ideas, this holomorphicity, then they come up with some solutions that very much reminiscent of, like, integrable systems, classical integrable systems. And there were some questions regarding, like, you know, the solution, but then people realized string theory provides this natural framework to study the supersymmetric theory. So here I'm trying to represent one aspect of string theory, which is string theory is a beautiful framework to study supersymmetric gauge theories that are simplified versions of theories you're interested in to understand. Okay? As I said, I mean, there are other motivations, so let me just, like, you know, say without, let me also, like, say in one slide. So they've been used also in phenomenology, as I said. So here is another example. If you let the coupling constants of different interactions run as a function of energy, they do not meet, but if you just, like, you know, invoke the minimal amount of supersymmetry, they just beautifully merge at higher energies. Even gravity is believed to join them at very high energies, and that's another motivation why superstring theory could be also a physical theory, that you have some supersymmetry in nature. Okay, so what do we know? So we know that there are 4 interactions in nature, so strong interactions, weak interactions, electromagnetism, and gravity. And as all of you know, that 3 of them can be combined under a single framework that's we call now standard model. So gravity is just like, you know, this annoying sibling that doesn't want to play along. And maybe, I mean, that's another thing about string theory, maybe string theory is the right theory to combine all the interactions under a single framework. And one of the promising things about that, if you look at any string theory, there is one particle that always pops out to you, and that's a graviton. That's a particle that you need to understand to quantum gravity. And it's not something you put by hand, it's just a theory that gives you that particle for free. So it's, in that sense, it's very natural that string theory could be the theory of quantum gravity. In addition, for its consistency, it has also like gauge symmetries in it. And these gauge symmetries are big enough that can accommodate standard models. So if we can be smart enough to understand how those symmetries break down to the energies we measure right now, and understand the important, the background, then we may actually see some physics coming out from string theory, but we haven't seen it yet. But I also want to emphasize, even if this theory is not the ultimate theory of nature, it has been teaching us some valuable stuff. So one of them is holography, right? I mean, holography has been used widely in many examples, and I'm just going to demonstrate one of them in which I was involved to you in a few slides. And also, I think Aziz is going to talk about it today. So it is useful, but it also is teaching something else, more fundamental. I mean, that's the most, for me, most important aspect of holography. I mean, it connects a theory that doesn't know anything about quantum mechanics to a theory that knows about quantum mechanics but doesn't know anything about gravity. So one theory is a gravitational theory, classical gravitational theory, and the other is quantum theory, quantum field theory. And holography tells you they're equal to each other. You see if the correspondence combines and gives you the dictionary how to translate some observables from field theory to the observables in gravity theory. So in that sense, I mean, also philosophically it's very deep. In addition to that, I mean, string theory teaches us how to couple gravity to gauge theories. That's also valuable. Maybe this is not the correct way, but that's one way. And we may actually find the correct way eventually. And moreover, one of the biggest successes of string theory is this black hole microstate counting, right? There is this beautiful formula by Hawking and Bekenstein, which relates the entropy of the black hole to its horizon, the area of its horizon. But that's like, you know, not like in first principle computation in the sense that entropy is related to microstate counting, but you don't know what to count. String theory can do that. So there's a beautiful paper by Sturminger and Baffa which shows us if you can engineer a certain external black hole and look at the states, which are just string states in that setup, you can count them, and if you look at the asymptotic behavior of this count, that reproduces this famous formula of Bekenstein and Hawking. So that's like, you know, the only probably way to get a microstate count for black hole entropy. So it's another beautiful result. So there are like, you know, many additional reasons that I'm not going to talk about today to study and understand string theory. Okay, so here is like a small outline. So I'm going to try to be brief. So I will just talk about, flash out in 2 minutes what string theory is. And as I said, give you two examples. So one of them is going to be this quark-gluon plasma and how one can engineer this in the ADS-CFT setup and do some computations. I will just like, you know, show you how an incredibly complicated problem that cannot be solved by any means is reduced to a problem of classical mechanics from sophomore year that you can just solve by you know, a page computation and plugging it into a computer. The last part is going to be a little more technical, but I'm going to show you another beautiful construction which goes under the name geometry engineering, and how one can understand some aspects of supersymmetric gauge theories that I mentioned before using this construction. Okay, so what is string theory? So it's simple. When we are talking about quantum mechanics, we take a particle and that particle traces a world line as time passes, and when we want to do quantum mechanics, we just sum over all possible paths, and that's the path integral introduced by Feynman. So what do? You say, well, I just take a point particle and think now it as a string. So here I just put a closed string, meaning it's just a loop. So that loop can evolve in time, and as it evolves in time, it traces a surface. Okay. And of course, now there is a huge difference between the point particle and strings, and one of them is since this is a sheet, two-dimensional object, there is also more interesting topologies. So you can have handles on this world sheet, so they will represent the interactions. So now you are dealing with another path integral that's a little more complicated, okay? And so then how do you get particles out of string theory? Well, if you just take a solid, right? It consists of atoms. We know that the atoms are made of protons and neutrons on their nucleus and electrons orbiting around them. And then the protons or neutrons are made of quarks. So there is this unification in string theory. Like they say, okay, if we have particles, they are just different vibrational modes of the same fundamental string. They are just different vibrations. So if it vibrates in one way, it produces you the electron. If it vibrates in another way, it produces a quark. So you have a unification. Instead of having this zero particles, you just have one fundamental string that just vibrates differently and gives you different particles, as if you get different notes from vibrating strings on and off. Okay, so then people realize, the strings should not be only closed loops, they can be also line segments. So if you have a line segment, so it's not going to trace anymore some sort of tubular thing, it's going to traverse a sheet, but then you have to introduce boundary conditions. So then people ask what the possible boundary conditions are. So if you do not want to break point invariance, if you just want to leave the symmetries of space-time invariant or intact, of course you have to impose normal boundary conditions on the ends of the strings. Because if you just say, well, the string ending on a specific point, that means in that direction you break the point invariance. You have a preferred plane on which the strings are attached. So people didn't want to live with that idea, but then soon realized, well, actually, this is a very good idea. People also should consider the Dirichlet boundary conditions, and the strings can end on what's now called the D-branes. So they are solitonic objects that are also present in string theory. So people realize actually string theory is not just the theory of strings, but it has also branes, membranes. And one excellent thing about this is, so the branes are charges for certain higher form fields in supergravity, and moreover, if you take a stack of branes, they engineer a gauge theory. So if you have n branes which are are placed on top of each other and extending in a number of space-time dimensions, that branes support a UN gauge theory. So this is also a beautiful way to understand gauge theories. So that's why people like the idea of D-branes, and thanks to Polchinski, we have a much better idea about what the D-branes are. And we will use them eventually. Okay? But so far, all the construction I've been telling you doesn't include any fermions. And that's a big problem because we know that in nature we have fermionic particles like electron or quark. So what should we do? So to introduce, in string theory also these fermionic particles. And again, the resolution came if you introduce supersymmetry on the world sheet of string theory. So here you have, you can also regard this as a two-dimensional sigma model coupled to some world sheet gravity. And to that theory, you introduce supersymmetry. And then you can ask the question, well, how many different ways I can do that? And it turns out there are in fact 5 different ways that you can add supersymmetry. And then you have this M theory. So in mid-90s, Witten thought, okay, if you have like 5 string theories, it's too much. If this is supposed to be, and I think people at that time were a little bit more confident about string theory being the theory of everything. So if string theory is supposed to be the theory of everything, 5 is a huge number, so you should reduce it. And as he was trying to reduce the number of string theories, he realized, well, there is actually M theory. Nobody knows what M stands for, magic, mystery, mother, inverse W. There are all kinds of speculations, but there is this M theory that's a non-perturbative completion of string theory. And another an important result, as you say, here I just also have some groups associated with the string theories. Also, another very important result in string theory is if you add supersymmetry on the worldsheet and compute the number of dimensions that string theory should live in, you get 10. So this is for quantum mechanical consistency of the theory. And let me elaborate on what I mean with quantum consistency. When you're writing the work line, you expect that work line to be parameterized in an infinitely different ways, but in each parameterization, you should get the same result. Likewise, if you parameterize the worldsheet, in each parameterization, you should get the same physics out of it, because that's your choice. That's not something intrinsically physical. So if you want this type of symmetry to also survive quantum mechanics, string theory picks a dimension. Says if you write me in quantum mechanically, if you quantize the classical strings, relativistic strings, then not only space-time dimensions in which the symmetries that you expect from your theory to survive is 10. Okay? So that's the number you have to live with. And that's interesting because I don't know any other theory which actually picks a space-time dimension. You can write electromagnetism in any number of space-time dimensions. The theory will have a different behavior, but it's consistent. You can write it down. String theory is not the case. But then you can immediately object. Well, we don't live in 10 dimensions. We have just 3 space dimensions at one time. So we live in a 4-dimensional space-time. Where are the remaining 6 dimensions? And I will try to elaborate on that at the end of my talk, okay? So the short answer is with the compactification, we assume those remaining 6-dimensional coordinates are so much smaller than anything we have observed so far. And of course, the other immediate question is, where is the standard model? If it's the theory of everything, it should have standard model. It should have this particle, it should be able to get these particles plus the Higgs boson, and also get the interactions and observe this, get the standard model of the string theory. And this is still an open question, unfortunately, even after 40, 50 years. But now I think, here we have to distinguish between 2 important questions. One of them is, does string theory really describe the universe? And that's related to the last question I asked. Can you get standard model of string theory? We don't know. We don't have any experimental evidence so far, direct or indirect, that supports the string theory is the theory of everything, or the theory of the universe. So it may not be. And it will be too bad, but that's life. The nature is the ultimate judge, whether your theory is the theory of nature or not. So the second question is, if the string theory is a well-defined and self-consistent theory, and the answer for that is yes. You can, there is a lot of evidence that that's true. One possible thing is you can, for example, take a physics problem, or take a string theory problem, solve it using the methods of string theory, and there is an analogous problem in math that mathematicians can go and solve the same problem with their own techniques in a rigorous way, and the answers match. And in many cases, so far, string theory was capable of teaching us new physics. As I said, how to couple gravity to gauge theories, how to count microstates in a black hole. So there are many examples. So we just the way I like to see it, or I justify myself, is it may not be the correct theory, but remember Lagrange and Hamiltonian, right? Those formulations were ingenious. They introduced, in a sense, new physics because they changed our point of view, but it didn't include anything more than what Newton had to say. However, if you didn't have Hamilton or Lagrange formulations, you would have a hard time to write quantum mechanics. So that was like, the gap to connect like, true theory of nature. So even if it's not the theory of nature, I'm hoping at least it will just be into some mathematical framework that will lead to the correct theory. Okay? Anyway, so maybe I should stop and ask if you have any questions. Okay, then let me just move on to quark-gluon plasma. So why is quark-gluon plasma important and why people have been spending so much time both on the experimental side as well as on the theoretical side? So one of the, what is quark-gluon plasma? If you just like, it's a state of matter in quantum dynamics when the pressure, when the density and temperature are incredibly high. They are so high, it's close to the beginning of the universe. It's just hundreds of milliseconds, again, microseconds of the Big Bang. So it's such a dense material. And people have been trying to reproduce in small scale this in laboratories at CERN and Brookhaven National Lab, where they collide either lead or gold nuclei. So they just crash them and they just put so much energy in a very small region. So they create, this is just a cartoonish picture. This is not very precise, but okay, it just gives you, you just create some quark-gluon plasma. And one of the most important problems to understand, maybe the evolution of the universe is if you have energetic particles that are moving in this plasma, how are they behaving within that plasma? Okay, how they are coupled to this plasma. It's a dissipative system that we have seen from experiments. It's not in equilibrium, and the system is strongly coupled. So when a quark moves through the plasma, we measure that the quark is strongly coupled. So if it's strongly coupled, then your probably favorite approach to such system, perturbation theory, doesn't work because it's strongly coupled. You can only use perturbation theory if the perturbation is weak. It's not. It's just a fact of life. Then you can just say, well, we have also developed methods which can also understand the strongly coupled systems, and numerically that's good enough, maybe. But this system is a dynamical system. It just moves in time, so it evolves. All this, if you want to compute the correlation function, it will be very hard to extract information from lattice simulations. So lattice simulations is also not very reliable if you want to tackle this problem. So what can you do? So what you can do is you can again search for a cousin theory that mimics, or that whose dynamic mimics the dynamics of QCD, at least in a region where you're interested. So that's like the high temperature region. Sorry, there's a typo. So at very high temperatures, the N=4 supersymmetric plasma, that's the maximum amount of supersymmetry you can put on a gauge theory in 4 dimensions without introducing gravity, because every time you put supersymmetry, you just create, as it was mentioned yesterday, bosons and fermions, and you just increase their spin. If you put too many generators, eventually you'll start creating particles that will have spin 2, and you don't want that. So you just want to go up to 3.5 and stop there. So that's why it's just, we can have at most 16 supercharges in 4 dimensions. That corresponds to N=4. So this theory is very rigid. You can only change its gauge group, that's it. But its hydrodynamic behavior at high temperatures is very close to QCD. So, okay, let's try to understand quark-gluon plasma in that setup. And then you have, again, this holography or ADS-CFT that comes to your rescue. Because according to this ingenious conjecture by Maldacena, N=4 theory is dual to the string theory, type 2B string theory on ADS background, ADS5 background. So here, the gravity background is a curved space-time is 5-dimensional, so we are interested in 4-dimensional theory, but we just go 1 dimension higher, and we are in 5 dimension, and our theory lives on the boundary. So our 4-dimensional theory is on the boundary, and then this, we have this transverse direction, which acts like energy scale. So it's another beautiful correspondence between gauge theory and gravity. For example, in gauge theory, you have renormalization group flow, right? The coupling constant is changing over energy scales. And this is being realized in string theory or in ADS-CFT setup as redshift if you have a black hole. So imagine you have a black hole here that tunes the temperature of your plasma, and if you go towards the black hole, you're redshifted. That redshift corresponds to renormalization group flow. So you have a completely classical phenomena that maps a completely quantum mechanical phenomena through ADS-CFT duality. So that's going to be our setup. So we have the gauge theory that lives on the boundary, and we want to somehow construct a quark moving in a plasma, and take that hard problem and convert it into a gravity problem and solve the gravity of classical problem. And that's easily doable. So to tune the temperature, you put a black hole in the ADS space, and you put some membranes, right? I mean, open strings needs to be attached to branes. So you put some membranes, and when you put them, determines the mass of the quark. So you can also tune the mass of the quarks. And then a string that is connected to this membrane, the brain is nothing but a meson. So it has a quark and anti-quark pair. And you can do some Gedanken experiments, or some thought experiments, where you just take these quarks and move them along, and that corresponds in ADS just the catenary problem. But now you are not solving the catenary problem on Earth, but on ADS background. Okay? So it's a little bit harder. It's like a one-dimensional object that you need to solve, but it's okay. And you have to solve it in a time-dependent fashion, but it's doable. You can just do it, and you can, for example, get the dissipation rate of energy as a function of velocity and temperature or coupling constant. Okay, so this is a result we obtained using ADS-CFT, and this result has been used in many papers for phenomenological models to really measure stuff at LHC in, let's say, Alice experiments or other experiments performed in different labs. Okay, so this is a very nice prediction that you can make out of string theory that is related to experiments. Of course, it doesn't show that actually this is the theory of quantum gravity, but it's a nice tool. That's what I want to emphasize. Okay, so let me just go on to the last topic. So I want to talk about geometric engineering of topological strings. As I advertised at the beginning, we want to understand QCD, right? I mean, QCD is a hard problem. There is, one example related to QCD that we can have some idea using string theory, but let's try to also understand confinement. Right? Confinement is, again, one of the holy grails in theoretical physics. And again, now we want to put some symmetries, additional symmetries to get analytic control. So in this case, we are not going to put 16 supercharges. And as I said, if you put 16 supercharges, your theory is two constraints, because the only thing you can change is the gauge group. We want to have more. We want to be able to change the gauge group, the amount of quarks we are putting. So we want to have a little bit more freedom. So if you give too much freedom, if you just look at the minimum amount of supersymmetry in the theory, then it's n equals 1. Unfortunately, you don't get enough analytical control. But if you put 8, the half of the maximal supercharge that you can put into your theory, then you get what's called n equal 2 theory. And n equal 2 theory is the right amount of supersymmetry, which allows you to choose your gauge group, amount of quarks and such, as well as you have analytical control. So it's been a long known result before even the theory was solved that the effective Lagrangian, so the Lagrangian that governs the low energy Lagrangian, can be written as derivatives of a simple function. Okay, and that's called the prepotential. So this is f, this curly f is what's called the prepotential. So if you know f, you can just take its derivatives and you can write down your effective Lagrangian. It's that simple. And people also knew how to write down prepotential. People knew it had 3 contributions. So the first one is 3-level classical part. So they knew they had one loop perturbative part, and it's been also a lucky result that the perturbation series truncates at one loop. all higher loops are identically zero because there is this perfect cancellation between the fermionic and bosonic contributions with minus and with different signs. They cancel each other perfectly, and you just have one loop computation. And people have done it, and they also knew that there are some non-perturbative contributions, which are instantons, that need to be added to prepotential as the third term. And they also knew the form. So this form was known in the blue box, except the important piece, this F sub case, what the coefficients are. So people didn't know what they are. So these coefficients had to be determined. So in, I think, 1994, Seiberg and Witten came with an ingenious solution to solve this problem. So the solution was, again, as I said, using complex structure of the theory. They said, okay, let's try to study the vacuum of the theory, the space that describes the vacuum of the theory. They realized this classically expected moduli space will lead to inconsistencies. They realized, okay, that has to be deformed in quantum mechanics. So they found the correct moduli space with 3 singularities on it. And they used an analog of electromagnetic duality to connect the behavior of this, like, of the theory around the singularities. So they kind of patched the theory. They knew the behavior around, like, the singularities, and they patched them in a consistent way to get the whole picture using holomorphicity. And what they said is, so F, what we need to find here, like to tell the effective Lagrangian, F can be written in such a nice form with, like, in terms of two functions. These are the photon and dual photon expectation values or scalars. So, and then they said, and this is the part I said that's very close to classical mechanics, they said A and AD can be computed using an external surface or an auxiliary surface. Nobody at the beginning knew anything about what that torus is. And at the torus, you have two distinguished, like, one-dimensional loops. One of them is what I call the alpha loop, and the other is the beta loop, right? So you cannot contract them without cutting them. So he said, well, if you integrate one form, a differential, just some d something, if you integrate that one form along these distinguished cycles, one of them gives you A, and the other gives you AD, and they also gave you specifically what lambda should be. So once you know A and AD performing these integrals, you can just go to this relationship between A and AD and determine what F is. So they managed to use this construction to get F. And of course, a month or 2 months later, physicists realized, well, this is like the way we solve classical integrable systems, and that's the spectrum curve. And then there was this beautiful research direction connecting gauge theories to integrable systems. And again, you see this is related to a quantum system is related to a classical system. Of course, although this theory, this solution is beautiful, it raises immediately two questions. So one of them is, what does the Seiberg-Witten curve mean? Is it just a gadget, or does it have anything physical meaning? Because you don't have a torus in R4. So the other question is, their solution is not a direct solution. So can we get a direct solution? And it turns out both questions can be answered affirmative. And let me start with the second question. Can we have a direct approach? And I will connect it to string theory at the end. So what do I mean by a direct solution? What was wrong? Nothing was wrong, of course, with Seiberg-Witten solution, but what do we mean by a more direct approach? So the more direct approach means, if we are talking about an instanton contribution, we are talking about an instanton solves a partial differential equation. So the self-dual part, anti-self-dual part should be, self-dual part of the curvature should be zero, should be vanishing. So it's a partial differential, you have to solve it. And it doesn't come with 1, 2, 3 solutions, it comes as families of solutions. And those families of solutions are described very complicated spaces which are called the moduli spaces. And even if you take the simplest non-abelian gauge group, let's say SU2, and you're looking at one instanton, that space is 8-dimensional. Okay, so it's just like they're like high-dimensional, complicated spaces, and they have some, of course, some complex structure and such, but they're hard. So, okay, so if you construct the modular space, how we can get the contributions of instantons, and let me give you an example. So imagine we solve this equation, and the modular space, which is never the case, let's say assume it's zero-dimensional. Zero-dimensional means our modular space, the space that describes the different instanton configuration, is just a collection of points. And if you want to get the contribution, you have to sum over points. Okay, if you don't have zero-dimensional space, if you have like a space, so you have to integrate over them. And the integrals are divergent, singular, I mean, they're very complicated integrals that people couldn't perform. So instead, what was done after Cyber-Newton solution, it's a program initiated by Losen, Moore, Nekrasov, and Shatashvili. They deformed space-time. And I don't want to go into the details of how they deformed it, but they introduced a non-trivial action on space-time. So there is a U1 squared, so two rotations that they introduced on space-time, and that action can be lifted to the modular space of instantons. So it means you can just take that action and lift it to a Lie group action on this modular space. And if you, I mean, this is the details of like, you know, if you have an appropriate space X with certain like, you know, Lie group action, mathematicians have developed a formula that says, okay, if you have such an integral over the whole manifold, you do not get contributions from every point, but rather than you get contributions from the fixed points of the group action. So they, instead of solving this integral, they deform the space-time, and they use a deformation to evaluate these integrals using these mathematical formulas from localization. And these are epsilon 1 and epsilon 2 are their deformation parameters. They're just angles, how much you rotate each plane of R2 in R4. And they could, like, you know, get this generating function Z, okay? So, and then they could show, or Nekrasov could show, if you turn off the deformation, right? Because I mean now we are doing this computation on a deformed space-time to match the Cyber-Newton theory. We have to turn off the deformation. So he's taking the limit to turn off the deformation, and this partition function, or this like generating function, reproduce Cyber-Newton solution. So this indirect approach and direct approach match beautifully later, but there is more to it. And let me talk about it more. So, as I said, string theory is 10-dimensional, and we live in 4 dimensions. So, how do we get from 10 dimensions, 4 dimensions? So, here is a cartoonish example. So, you start with R2, let's say in 2-dimensional space. So, you can compactify, you can identify this minus infinity to infinity, and make a cylinder out of it. And you can take the cylinder as a line, and over each point of the line, there is a circle. So if you just like imagine a circle, about every point on this line, actually that's a cylinder. So if the radius of this circle is very, very small, that your eye cannot distinguish, then it just appears like a line. Like the power lines that you see, they appear like one-dimensional, but if you just go closer, you just see it's a cable that's 3-dimensional. So dimensionality is, in a sense, at least with our measurements, it's just a matter of how close you look at. For example, in my electromagnetics courses, I always give this example. If you have a compact charge distribution, and if you look at the charge away from any away at a distance that's much larger than the size of the object, it reduces the point particle. It acts like a point particle for any measurement. Of course, you have some leading corrections, but if you cannot measure that accurately, that charge distribution is a point particle to you. So it's more or less the same idea. So here, what do we do? Instead, like we have like instead of R2, now we have R10, and this S1 that I use as compactification manifold. Now I have a 6-dimensional space, and for technical reasons, it has to be Calabi-Yau to have supersymmetry and consistency in your theory. So it has to be Calabi-Yau, and this R1 now is R4. So we just started a 10-dimensional theory, then compactify on a Calabi-Yau threefold, which is 6-dimensional. So 3 refers to complex number of dimensions, or complex dimensions, and then you get a 4-dimensional theory. And the physics in that 4 dimensions is dictated by the 6-dimensional manifold. How is that? So you have certain set of information. What your theory is. You have to tell me what your gauge group is. You have to tell me whether your theory is asymptotically free. You should tell me the quarks. You should tell me like how much supersymmetry you have to preserve. So you give me a list. And geometric engineering, it's a program, I think, by Kozcaz and Wafa. They said, well, we can actually engineer this. So I mean, we can encode the information about the gauge group into the singularity of what's known as K3 surface. That's a 4-dimensional surface. So here I'm just depicting AN. So AN is a singularity that you have like, the spheres are touching each other like on a necklace. But this is still like 4-dimensional, so we are down to 6 dimensions. So we have to further compactify on a 2-dimensional space, and they are classified by their genera. And then people say, well, if you go to a higher dimensional genus, you start adding many multiplets, you lose asymptotic freedom. So you want to preserve asymptotic freedom, you have 2 choices. It should be the genus 0 or genus 1. And then depending on which one you put, you either have like, n equals 2 supersymmetry with 8 supercharges, or n equals 4 with 16 supercharges. So to study supersymmetry, to study cybermeter theory, we have to pick P1. So it's just a sphere. Okay? So then you gave me like K3 with singularity. So here let me emphasize, if you have an SUN gauge theory, you can write down the Lagrangian. But imagine you have a theory with an E6 or E7 gauge group. Can you write down the Lagrangian for it? No. But you can still engineer them within string theory. You can engineer a gauge theory with E6 or E7 gauge symmetry. And let me give you a simple example. So if you want to look at SU2 theory, then this is called then the geometry is just a cartoonish picture. This is what's called the toric diagram of local P1 cross P1. So this base stick, the edge of this rectangle B represents one of the P1s. So it represents the P1 here on the base, and the vertical one represents the P1 that is inside the K3. So this is just like a cartoonish picture to represent. So I have a 1 P1 here, 1 P1 here, it's just P1 times P1. It's just some sort of non-trivial vibration though. So here is the interesting thing to the first question I asked. So this construction lives in one of the string theories that's called type 2A. You can take the mirror symmetry and you go to type 2B, and then you can there is another clavia that's mirrored to the initial one, and that has some base curve. And that base curve turned out to be exactly the Seiberg-Witten curve that I showed you here. That curve turns out to be part of space-time that is used to compactify in type 2B string theory setup. So this object which was which was an auxiliary object, just a gadget, turned out within string theory just part of space-time. So they discovered actually by doing a gauge theory analysis something that lives in string theory. So what can you do? So there is a beautiful correspondence they found. So if you define a simpler string theory, that's called the topological string theory, that's just from the worldsheet, not to 10-dimensional space, but to a 6-dimensional target space. And remember, 6 was also the number of dimensions we needed to compactify. You can just sum over holomorphic maps, that's a requirement, again, that's imposed by your theory. If you just do that, you get topological strings. And the funny thing is, remember this localization computation by Losev, Mu, Shatashvili, and Nekrasov. So in that computation, Nekrasov realized an amazing relationship. He said, if in this limit that I'm taking epsilon 1 plus epsilon 2 is equal to 0, so he just couples these 2 rotations to each other, and this 2 degrees of freedom reduced to 1, because we impose a relation between them, and you can associate one of the parameters to the coupling constant of string theory. And if you look at this instanton generating function here, okay, you just take this, you impose this limit, and make an expansion epsilon 1. That expansion is precisely the expansion that you encounter in topological string theory. That's basically genus expansion. And if you look at the lowest genus contribution in topological string, that gives you the prepotential. So what you can do is you can tell me the theory you want to study. Geometric engineering tells me on which space I have to reduce my theory from 10D to 4D, and then we do a topological string computation. And if we do the genus expansion, the initial starting thing gives me the low energy effective action. So from topological string that's been first initially introduced as an academic theory, that actually tells you something about low energy dynamics of supersymmetric theories. Then the question is, how do we compute them? Also, let me tell you another thing. This is like a beautiful result by Gokokuma and Wafa. They realized this F, topological string theory F, also encodes in a nice way the particles in your theory. What do I mean with particles? You have instanton particles, you have W bosons, and you should ask like, how I can get those particles in string theory. Well, it's easy. Here I have like the space with like a bunch of spheres, and I have like what's called the D2 branes. These are actually three-dimensional objects. So this refers to the space dimensions, not time. So this is a three-dimensional object, and you can wrap them on this different two-dimensional submanifolds or subspaces. So if you take a three-dimensional object, wrap on a two-dimensional object, then you have one dimension left. And that extends in R4 as the world line of the particle. And the masses or the charges are determined by the area or by the volume of this spheres. So you have also a beautiful realization of W bosons or instanton particles using V-branes and using geometry. And this partition, this amplitude, or the topological string amplitude, actually is the generating function for those different particles. So you can compute F, and Gopokuma and Wafa tells you this has a unique expansion up to this like unknown integers. So you can, if you compute this F, then you can read off like this integers, and they give the degeneracies for given particles of mass and with certain like spins. So you can also like have information about the content or your particle content. So how do we do that? So we do that by just realizing every manifold can be composed into patches of C3 if they are patched in a nice way. So this is like, how can you imagine like C3? So here is a nice way of thinking about it. You can either just say, okay, it's Z1, Z2, Z3, or you can just say, I think in terms of polar coordinates for each coordinate, so one absolute value and the angle. So you draw like the absolute value, so this is the first octant of R3, and each point you imagine you have three circles, so it's a T3. But if you just go to the wall, so one of the R's shrinks, so one of the circles shrinks, then you have like a torus, and if you go to edge, you have like two of them are 0, so you have a circle. If you go here to the origin, everything shrinks, you have a point, and actually you have like one way to think about it. In addition to four-dimensional substructures, you have this disk coming out of each edge. Okay, and then to compute for SUN theories, there is a beautiful formalism that goes under the name topological vertex. That's actually this amplitude. So compute the amplitude for C3. Okay, and these coefficients are nothing but what we call the topological vertex. And if you know how to glue them, you're done. So that's the vertex, and that's the previous example. So here we have this cartoonish picture for local P1 cross P1. So now you see there are all these like three-dimensional vertices. If you know the contribution, so you just take 4 of them, put them together, and glue them. We have a gluing algorithm. You glue them. If you glue them, you can just get the topological string amplitude. And if you expand it by expanding like with respect to different curves, as I promised, you can get all kinds of particle content of the theory. And you can get the prepotential, you can get the particles, and it also gives you gravitational couplings of the theory within the string theory. So you learn not only what gauge theory has to offer to you, but much more if you embed the same problem within the string theory. Some structures that appear ad hoc, not known, become part of space-time, And recently there are a number of different constructions how to engineer gauge theories, and people found beautiful relationship between four-dimensional theories, two-dimensional theories, classical systems, integrable systems, how to quantize them. So string theory offers a lot, also in different directions that people are not expecting a priori from gauge theories. And this is where I want to stop. So thank you very much for paying attention.
I have one. Now the mankind has very advanced devices like Assoc.
Yeah.
Is there any signal about the existence of supersymmetry?
No, not that I know of. And their search, as far as I know, is very general in the sense that they are not searching for a specific theory. What they do is they first compute what they should expect to see in the detector with the non-physics, and then search whether there is an excess on top of it. And that's in a sense very general. It doesn't assume any particular model. But okay, so for supersymmetry, I think the parameter space, especially for the minimal supersymmetric model, is just covered, they didn't see anything. But okay, so then there is this huge discussion whether we should build D1, which is 100 TeV. There is a proposal that CERN is going to build a much bigger accelerator. Yeah, people argue we should build them or not. Or there are also questions whether there could be long-lived particles. So long-lived particle could be you have the collision, the particle is created, but escapes the detector and then decays. And you didn't trigger for it. Or you don't have detector set up for it. So I think one proposal was to build detectors at the top of the pit, right? There is a pit where they lower the components. So I think they are even considering build detectors on the surface of Earth. So if there is a long-lived particle, it may decay in the pit, and when it decays, then those particles can be captured. So I think I heard one thought also challenging. I'm not sure whether this is for supersymmetry alone. This could be also for other particles or for other theories. But if supersymmetry is discovered, of course, I think string theories are going to be very happy, or the extra dimensions. There is also no proof for extra dimension.
So that's clear.
Oh, there's a yeah.
No, sorry. Ask a question. What are the implications of extra dimensions? Maybe if they are real, in CERN they are trying to manipulate the space and time and graviton to send to other dimensions.
I wouldn't go that far yet. Don't know how to manipulate space-time. Black holes, when they merge, they deform. We have seen it, gravitational, but I'm not sure how to manipulate. But okay, there could be different scenarios. One of them is the way I was talking about. You have in a very small extra dimensions. Well, they're just in a regular dimensions, like the one we have seen, but they're just small, they're just compact. The other possibility is, which could be more exciting, is we might be living on a brain, right? There's a brain and all the we are stuck on this brain and that's embedded. That's just like a slice of bread in the ambient space. And we are stuck to that. So there are different kind of scenarios. They can explain different things. For example, the latest scenario can explain why gravity is so weak compared to other interactions, because all the interactions are confined in the brain, and gravity leads to whole space-time. That's why it's much weaker. But there is nothing conclusive yet. I hope there is. In my lifetime, that would be amazing.
Okay, referring to your first introduction to string theory, I'm going to ask very silly question. I think that is the origination of string theory. If we consider now, you already passed the.
Oh, yeah, I did.
Anyway, I think if I ask.
So go ahead.
Yeah.
Okay.
If the way actually the string behaves gives the different particle, as you said here. We have a few number of particles in the nature. In very simple sentence, what keeps them to vibrate in finite number of modes, not infinite? Because
It takes energy. If you excite most, it requires energy.
So you mean we have few number of particles because we don't have energy to create them?
No, I'm just saying, if you, the heavy particle is distinguished from a light particle by the vibration modes you're exciting. Because once you excite each mode, it costs energy. And that's why you have massive particles and light particles. And if you excite too many, then they just become, you should also take into account, they immediately become string scale. They just become supermassive.
Understood. And just the last part, what keeps the string to remain a string? Again, with simple language.
Oh, nothing. One thing, what keeps a string?
They are closed, let's say, the particles.
Right, but there is a close-open duality. For example, you may have an open string whose ends can merge together and becomes a closed string and can leave the brain.
Understood.
And then that's the gravitational interaction. That's how it interacts. For example, the brain, it exchanges closed strings. So open string you cannot have only open strings, for example, because an open string, the ends can merge and create a closed string. And that's why, for example, graviton is a closed string. That's why in every string theory you have to have, you cannot write just a theory of open strings where you don't have closed strings and no graviton, it's impossible. That they merge and or strings can merge together. This is the worksheet. They can, for example, this handles, so you have one open closed string coming in, so it can merge into two and recombine.
Understood.
So, and these are the interactions, these are the scattering of string states.
Thank you very much.
That's clamp.
Thank you.